Forecasters at the Storm Prediction Center in Norman, Oklahoma, have been watching the same stretch of atmosphere for days now, tracking a front that's expected to settle in somewhere across the Central Plains and Midwest before sagging into the southern Mid-Atlantic later this week. And every model run keeps painting the same uncomfortable picture. Moderate to strong destabilization building right along that boundary, deep moisture pooling underneath it, and the kind of setup that meteorologists describe carefully in technical language, precisely because the plain English version tends to sound more alarming than they're willing to commit to this many days out. But strip away the hedging, and what's actually developing is the ingredient list for exactly the kind of severe weather outbreak that has, in past years, produced long-track tornadoes, destructive straight-line wind events, and flash flooding, severe enough to overwhelm entire drainage systems in a matter of hours. So today, we're going to walk through exactly what's forecast to happen, why this particular kind of atmospheric setup is the one meteorologists genuinely worry about more than almost any other, how this year's severe weather season has been shaping up differently than in years past, and what the actual science says about how seriously you should be taking a forecast like this one. Before we get into it, I want to be clear about the tone here, because severe weather content online swings wildly between two extremes, either treating every storm system like an apocalypse to farm views, or downplaying genuine risk to avoid sounding alarmist. We're aiming for neither. We're going to walk through what the National Weather Service and the Storm Prediction Center, the federal agency responsible for forecasting this exact category of hazard across the entire country, are actually saying in their own technical discussions, and translate that into something you can actually use to understand your own risk. If that sounds useful, drop a comment letting me know what part of the country you're watching from, because I read every one of them, and if you want to stay ahead of how this specific setup evolves over the coming days, now's a good time to subscribe, because forecasts like this one tend to sharpen considerably as the event gets closer. Let's start with what's actually driving this particular setup, because understanding the underlying ingredients is the difference between a headline that sounds scary and actually knowing whether you should be paying close attention. Severe thunderstorms don't form randomly. They require a specific combination of atmospheric ingredients coming together in the same place at the same time, and meteorologists have spent decades refining exactly how to identify when that combination is likely to align. The first ingredient is instability, essentially how much energy is available in the atmosphere to fuel explosive upward motion once a storm gets going, measured using a value called convective available potential energy, or CAPE. Think of CAPE as the fuel tank. Warm, humid air near the ground wants to rise because it's less dense than the cooler air above it, and the bigger the temperature contrast between that warm surface air and the cooler air aloft, the more violently that rising air accelerates once it breaks free, similar to how a hot air balloon rises faster. The greater the temperature difference between the air inside the balloon and the air outside it. Values above roughly 2,000 joules per kilogram are generally considered strong, and forecasters have flagged the potential for values well above that threshold building along this front later in the week. The second ingredient is moisture, because without enough water vapor in the lower atmosphere, even a highly unstable environment won't produce much beyond weak, disorganized storms. This is why forecasters pay such close attention to dew point temperatures. Since a dew point in the upper 60s or into the 70s, Fahrenheit indicates genuinely humid, storm fuel-rich air at the surface, exactly the kind of moisture currently expected to pool beneath the frontal boundary tracking across the central United States later this week. The third and arguably most critical ingredient, the one that separates a garden-variety thunderstorm from something capable of producing long-track tornadoes or damaging straight-line winds, is wind shear, meaning how much the wind's speed and direction change with height above the ground. When winds near the surface are blowing from one direction, while winds a mile or two up are blowing faster and from a different direction, that difference imparts a rotating motion to the atmosphere, essentially laying a horizontal tube of spinning air across the landscape. If a strong enough updraft within a developing thunderstorm manages to tilt that horizontal spin into a vertical orientation, you get a rotating updraft, the defining feature of what meteorologists call a supercell, the specific storm structure responsible for the overwhelming majority of the strongest, most destructive tornadoes recorded anywhere in the world. A supercell's anatomy is worth understanding a little further, because it's exactly what forecasters and storm spotters are trained to recognize the moment conditions, like this week's setup, start producing real storms on radar and in the sky. Once that rotating updraft, called a mesocyclone, becomes established, the storm develops a genuinely distinctive structure, a persistent rotating column of rising air often visible on radar as a hook-shaped echo curling around the storm's back edge. The signature meteorologists watch for as one of the clearest visual indicators that a storm has organized enough to potentially produce a tornado. As the mesocyclone tightens and intensifies, often aided by a surge of rain-cooled outflow wrapping around the updraft's base, A smaller, more concentrated area of rotation can develop right at ground level, and it's that final tightened rotation that ultimately produces the visible funnel cloud, and, if it makes contact with the ground, an actual tornado. This entire process, from a broad, storm-scale mesocyclone forming aloft down to a tornado actually touching the ground, can unfold in as little as 10 to 20 minutes under the right conditions, which is exactly the kind of narrow window modern Doppler radar and trained spotter networks are specifically built to catch as early as physically possible, since every extra minute of lead time directly translates into more people reaching shelter before the tornado itself arrives. The fourth ingredient, a lifting mechanism, something that actually forces all that unstable, moist air upward in the first place, typically comes from a front, a dry line, or an area of low pressure. And in this case, forecasters have specifically pointed to the front itself sagging southward through the plains and Midwest as the trigger mechanism that could focus storm development right along its length. When all four of those ingredients come together in the right proportions, and forecasters at the Storm Prediction Center are watching precisely this kind of alignment develop later this week, you get what meteorologists sometimes refer to informally as a classic setup, the same underlying combination responsible for essentially every major severe weather outbreak in recorded history. It's worth being honest about the uncertainty involved here too, because that's exactly what the forecasters themselves are saying. The Storm Prediction Center's own extended outlook has specifically noted considerable uncertainty regarding the exact position of the frontal boundary several days out, which matters enormously, because a shift of even 100 miles in where that front ultimately settles can be the difference between a dangerous outbreak, affecting a heavily populated corridor, and a comparatively unremarkable, more isolated, severe weather day. That uncertainty isn't a weakness in the forecast. It's an honest reflection of how the atmosphere actually behaves this many days in advance, and it's exactly why meteorologists sharpen their language and their confidence as an event gets closer, rather than locking in dramatic predictions 5 or 6 days ahead of time. This year's broader, severe weather season adds useful context for understanding why forecasters are watching this particular setup with extra attention. According to AccuWeather's long-range forecasting team, the 2026 season has been shaping up meaningfully differently than last year's exceptionally active stretch, which produced some of the most headline-grabbing tornado outbreaks in recent memory. This year, overall tornado counts are expected to land closer to the historical average of around 1,225 annually, somewhat below last year's total, largely because the La Niña pattern that had been suppressing some of the atmospheric conditions favorable for classic tornado outbreaks faded relatively quickly. But meteorologists have been explicit that a quieter tornado count doesn't translate into a quieter season overall. As that La Niña influence eased, conditions became more supportive of a different kind of severe weather threat. Thunderstorm complexes capable of producing extreme straight-line wind gusts, large to giant hail, and the kind of intense slow-moving rainfall that triggers flash flooding, severe enough to overwhelm rivers, storm drains, and low-lying roads within a matter of hours. One AccuWeather meteorologist put it plainly earlier this year, warning that people shouldn't let their guard down this severe weather season, and that flash floods and damaging wind gusts can be just as destructive as tornadoes, often impacting a much larger geographic area in the process. Flash flooding deserves its own explanation here, because it's frequently the most underestimated hazard tied to exactly this kind of setup, and it's also one of the leading causes of weather-related fatalities in the United States in any given year, more than tornadoes in many recent years when totaled nationally. The mechanism is fairly intuitive once explained properly. When a slow-moving or repeatedly regenerating cluster of thunderstorms parks over the same general area for an extended period, a phenomenon meteorologists call training, because individual storm cells move over the same location one after another, like train cars passing the same point on a track, enormous quantities of rain can fall on the same relatively small watershed within just a few hours. Urban and suburban areas are often hit hardest, not necessarily because they receive more rainfall than rural areas, but because pavement, rooftops, and other impervious surfaces prevent water from soaking into the ground at all, forcing all of that rainfall into storm drains and low-lying roadways that were often engineered decades ago for rainfall totals far lower than what a modern extreme thunderstorm complex can produce in a single afternoon. This is precisely why forecasters have specifically flagged flash flooding as a major concern tied to this year's overall severe weather pattern, since the same atmospheric conditions capable of producing damaging straight-line winds, deep moisture, and a slow-moving or repeatedly triggering frontal boundary are frequently the exact same conditions capable of producing training thunderstorm complexes that dump extreme rainfall totals over the same communities repeatedly within a short window. That shift toward wind and flooding as the primary threats this year connects directly to a specific and genuinely underappreciated hazard worth understanding in detail, because it's exactly the kind of event this current setup has the ingredients to potentially produce: a derecho. A derecho is a widespread, long-lived, fast-moving band of destructive straight-line thunderstorm winds, formally defined as a corridor of wind damage extending at least 400 miles, with wind gusts reaching at least 58 miles an hour sustained across that entire path, and frequently reaching well over 100 miles an hour in the most intense cases. Unlike a tornado, which strikes a relatively narrow defined path and moves on within minutes, a derecho behaves more like a hurricane's destructive core stretched out across an entire region, sweeping through community after community over the course of many hours, sometimes lasting the better part of an entire day, as it tracks hundreds of miles across multiple states. The most destructive recent example struck the Midwest in August of 2020, tearing across Iowa, Illinois, and several neighboring states with wind gusts that reached as high as 140 miles an hour in some locations, comparable to the winds inside a strong Category 4 hurricane. That single event flattened millions of acres of corn and soybean crops just weeks before harvest, destroyed grain storage infrastructure across the region, and ultimately caused an estimated $11 billion in damage, making it one of the costliest thunderstorm-related disasters in modern American history, despite never technically being classified as a hurricane or a widespread tornado outbreak. The mechanism behind a derecho helps explain why they're so uniquely dangerous, and in some ways harder for the public to properly anticipate compared to tornadoes. They typically form when a cluster of individual thunderstorms organizes into what's called a mesoscale convective system, essentially a large, self-sustaining complex of storms that develops its own internal circulation. As that complex matures, a pool of rain-cooled air sinking out of the storm spreads outward along the ground ahead of the system, and under the right combination of strong wind shear and instability, exactly the ingredients currently expected along this week's frontal boundary, that outflow can accelerate and organize into a bow-shaped line of storms, visible clearly on radar as a distinctive curved arc. The leading edge of that bow is where the most extreme sustained straight-line winds occur, and because the entire system moves as a cohesive unit rather than producing isolated narrow damage paths the way individual tornadoes do, a derecho can inflict tornado-strength wind damage across an area many hundreds of times larger than any single tornado could ever cover in the same amount of time. Understanding how forecasters communicate risk level for events like this is genuinely useful context worth walking through, because it's the exact system in play for the outlook currently covering this week's setup. The Storm Prediction Center uses a 5-tier system for its convective outlooks, ranging from marginal, the lowest category, indicating isolated severe storms are possible but not widespread, up through slight, enhanced moderate, and finally high risk, the rarest and most serious category, reserved for situations where forecasters have high confidence in a significant, potentially historic, severe weather outbreak. An enhanced risk, the category that portions of this week's setup have already reached in preliminary outlooks, indicates numerous severe storms are expected, with a greater likelihood of stronger, more organized, longer-lived storm structures, exactly the kind capable of producing significant tornadoes, large hail, and damaging wind swaths rather than isolated, short-lived cells. It's worth noting these categories tend to escalate as an event draws nearer and forecast confidence sharpens, which is exactly why meteorologists urge people not to assume a marginal or slight risk. Several days out means the threat won't grow more serious, as better data comes in closer to the actual event. It's worth grounding all of this technical explanation in what these setups have actually produced in the past, because the historical record makes clear exactly why meteorologists take this specific combination of ingredients so seriously. The super outbreak of April 2011 remains the benchmark event most severe weather scientists reference when discussing worst-case scenarios, a 2-day sequence that produced over 300 tornadoes across the southeastern and eastern United States, including a catastrophic EF5 tornado that tore directly through Tuscaloosa and Birmingham, Alabama, killing over 320 people across the entire outbreak and causing more than $10 billion in damage, making it one of the deadliest tornado outbreaks in American history. A month later, an EF5 tornado struck Joplin, Missouri directly, killing 158 people and destroying roughly a third of the entire city in under 40 minutes, a single tornado responsible for more direct fatalities than most entire tornado seasons combined. 2 years after that, an EF5 tornado tore through Moore, Oklahoma, a community that had already been struck by a devastating tornado less than 15 years earlier, killing 24 people and flattening 2 elementary schools in the process. Every one of those catastrophic events shared the same underlying ingredient list we just walked through: extreme instability, ample low-level moisture, strong wind shear creating rotating supercells, and a triggering mechanism, whether a front, a dry line, or a squall line, focusing that energy into an organized, sustained outbreak rather than scattered, short-lived storms. It's worth going back even further because the 2011 super outbreak wasn't actually the first event to earn that specific designation. The original super outbreak struck on April 3rd and 4th of 1974, producing an almost unbelievable 148 confirmed tornadoes across 13 states in roughly 16 hours, including several rated F5 on the original Fujita scale used at the time, killing over 300 people and injuring more than 5,000. What makes the 1974 event particularly relevant to any discussion of modern forecasting is the contrast in warning technology available then versus now. Doppler radar, the technology that allows meteorologists to directly detect rotation within a thunderstorm before a tornado even forms on the ground, didn't exist in any operational capacity in 1974. Warnings, when they came at all, relied heavily on visual spotter reports and older conventional radar that could show precipitation intensity but couldn't directly reveal the internal wind patterns inside a storm. Today's network of dual polarization Doppler radars, combined with a nationwide system of trained volunteer storm spotters and increasingly sophisticated computer modeling, gives forecasters the ability to detect a rotating mesocyclone, the broader rotating region within a supercell that can eventually spawn a tornado, often 10 to 20 minutes or more before a tornado actually touches down, lead time that simply didn't exist for the communities caught in the path of the 1974 outbreak. That improvement in detection technology is precisely why modern outbreaks involving a comparable number of tornadoes, while still often deadly, rarely approach the death tolls recorded in events from the pre-Doppler radar era, even when the underlying meteorological ingredients are just as extreme. None of that history means this specific week's setup is guaranteed to produce anything approaching that scale of catastrophe. And it's important to be precise about that distinction, because the vast majority of enhanced or even moderate risk days never come close to the severity of an event like the 2011 super outbreak. What that history does explain is exactly why meteorologists react with heightened seriousness the moment they see this particular combination of ingredients aligning: strong instability, deep moisture, significant wind shear, and a clear lifting mechanism, because it's precisely the same recipe that has, on the relatively rare occasions when every ingredient maximizes simultaneously, produced the deadliest severe weather events in the country's recorded history. It's also worth understanding the practical difference between a watch and a warning, because confusion between the two remains one of the most common and genuinely dangerous misunderstandings the public has about severe weather alerts, and it becomes especially relevant during a multi-day setup like the one currently being forecast. A severe thunderstorm or tornado watch means conditions are favorable for that type of severe weather to develop within a defined area over the coming hours, essentially telling you it's time to stay alert, keep an eye on the sky, and make sure you have a reliable way to receive further alerts. A warning is a fundamentally different, far more urgent message, meaning a severe thunderstorm or tornado has actually been detected, either by radar or by a trained spotter or law enforcement observer on the ground, and is happening or imminent in your specific location right now, meaning it's time to take immediate protective action rather than simply staying alert. That distinction carries real practical weight this week specifically, since a multi-day setup like this one typically means watches get issued well ahead of time across a broad area, giving people a genuine window to finalize their preparations, while the warnings that matter most, the ones demanding immediate action, tend to arrive much closer to when individual storms actually organize and begin producing confirmed rotation or damaging winds on radar. Watches are typically issued hours in advance and can cover large multi-state areas, while warnings are issued for much smaller specific zones and are meant to be acted on immediately, typically giving residents anywhere from several minutes up to perhaps half an hour of lead time, depending on the type of storm and how quickly it's moving. Tornado intensity itself gets measured using the enhanced Fujita scale, running from EF0 up through EF5, based primarily on a damage survey conducted after the fact, rather than a direct wind speed measurement taken during the event itself, since accurately measuring wind speed inside an actual tornado remains extraordinarily difficult and dangerous. An EF0 tornado produces winds in roughly the 65 to 85 mile an hour range, capable of snapping tree branches and causing minor roof damage, while an EF5, the rarest and most violent category, involves wind speeds exceeding 200 miles an hour, capable of completely leveling well-built framed homes and stripping bark from trees, the exact scale of destruction documented at Joplin and more. It's worth noting that the overwhelming majority of tornadoes that touch down in any given year fall into the weaker EF0 to EF1 range, and only a small handful of the most violent long-track tornadoes each year reach EF4 or EF5 intensity. But those rare violent tornadoes are responsible for a wildly disproportionate share of the total fatalities recorded nationwide, which is exactly why forecasters pay such close attention to the specific ingredients, particularly wind shear and instability working together, that are most strongly associated with producing that rarer, more violent category of storm. That last point is genuinely worth sitting with, because it's exactly why a forecast flagging strong shear alongside strong instability, the precise combination currently expected along this week's frontal boundary, carries more weight in a meteorologist's mind than a forecast showing high instability alone. Extreme instability without much shear tends to produce disorganized, pulse-type thunderstorms, capable of locally intense rain and hail, but generally lacking the sustained rotation needed to spin up a long-track, violent tornado. It's the pairing of both ingredients simultaneously, not either one in isolation, that historically correlates most strongly with the kind of organized supercell activity responsible for the rare but devastating EF4 and EF5 tornadoes that dominate the historical fatality statistics. And it's precisely that specific combination forecasters have flagged as increasingly likely to align along this week's boundary as the event draws closer. Bringing this back to the specific setup unfolding this week, it's worth walking through the regional pattern forecasters have been tracking across the broader 2026 season because it gives useful context for who tends to be most exposed to this kind of threat. AccuWeather's seasonal outlook has specifically flagged the corridor stretching from Texas through Alabama as facing the highest hail risk this year, with a secondary hotspot centered around Iowa, northern Missouri, eastern Nebraska, and northeastern Kansas, a stretch of the country that has already seen an unusually active severe weather pattern build throughout the year. The National Weather Service office covering the Chicago region, for example, had already logged an unusually high number of enhanced risk or higher outlook days earlier this year compared to typical seasonal averages, along with a record pace of severe thunderstorm and tornado warnings issued through the same period, evidence that this broader pattern of frequent, organized severe weather has been building well before this specific week's setup came into forecast range. That regional pattern matters because it means communities across a wide swath of the central and eastern United States have already had a season's worth of practice responding to serious severe weather alerts, which, if anything, tends to improve how quickly and effectively people respond when the next serious setup, like this one, actually arrives. Emergency managers in many of these repeatedly affected counties have also used the season's frequent watches and warnings as informal, real-world drills, refining local siren activation procedures, shelter locations, and public communication messaging in ways that tend to pay off precisely during a higher stakes multi-day setup like the one currently being tracked. So what should someone living anywhere near the forecast area for this week's setup actually take away from all of this? The honest, calibrated answer sits exactly where a responsible forecast should sit, taking the threat seriously without assuming the worst-case historical comparisons are the most likely outcome. The specific ingredients meteorologists have flagged, building instability, deep moisture, and strong wind shear converging along a frontal boundary with real but still uncertain positioning, are genuinely the combination associated with organized, potentially significant severe weather, up to and including the possibility of strong tornadoes, damaging wind events, or even a derecho-style wind episode if the atmosphere maximizes in the way current guidance suggests it could. But the exact location, timing, and ultimate severity remain genuinely uncertain this many days out, which is precisely why the Storm Prediction Center itself has been careful to frame this as an evolving, still developing forecast, rather than a locked-in certainty. The single most useful thing anyone in the potentially affected region can do right now isn't panic, it's preparation. Making sure you have a reliable way to receive weather alerts that doesn't depend solely on a phone that might lose signal or power during an actual event, identifying the safest place in your home or workplace to shelter if a warning is issued, and simply paying closer attention to forecast updates over the coming days as meteorologists sharpen their confidence the way they always do as an event draws nearer. That preparation checklist is worth spelling out a little further because the specifics genuinely matter when a warning actually arrives with only minutes of lead time. A basement or an interior room on the lowest floor, away from windows, with as many walls as possible between you and the outside, remains the standard recommended shelter location for a tornado warning and for anyone in a mobile home or a structure without a solid foundation. Identifying a sturdier nearby building in advance, rather than trying to figure that out once a warning is already sounding, can genuinely be the difference that matters most. For flash flooding specifically, the guidance that emergency officials repeat every single year exists precisely because so many flood fatalities involve the same avoidable mistake, driving into water covering a roadway, since it takes only about a foot of moving water to sweep a typical passenger vehicle off the road entirely, and floodwater depth over a road surface is notoriously difficult to judge accurately from inside a moving car, especially at night or in heavy rain. That single behavioral pattern, more than any other factor, is why flood fatalities remain so stubbornly persistent year after year, despite advanced warning systems that, in most cases, gave drivers ample notice that heavy rainfall and rising water were already underway in their area. There's a broader pattern worth sitting with here too. one that connects this week's specific forecast to the way severe weather risk actually works across an entire season rather than a single event. Setups like this one don't appear in isolation. They tend to arrive in clusters, tied to the same broader large-scale weather patterns. In this case, the transition away from a suppressing La Niña influence toward conditions more favorable for organized severe weather that meteorologists have been flagging as a defining feature of this particular season since well before this specific week's forecast came into range. That means a setup like the one currently being watched isn't necessarily a one-off anomaly. It's arguably a natural extension of exactly the kind of active wind and flooding-focused pattern forecasters predicted for this year months in advance, which is precisely why staying informed through an entire severe weather season, rather than only reacting to whichever individual forecast happens to generate the most alarming headline, tends to be the far more useful long-term approach for anyone living in a region genuinely exposed to this kind of risk. It's also worth remembering that meteorology, for all its sophisticated modeling and decades of accumulated historical data, remains fundamentally a science of probabilities rather than certainties, particularly at the multi-day range this current forecast is still operating within. The same models flagging this week's setup as potentially significant are constantly ingesting new data, fresh satellite imagery, updated weather balloon soundings, and refined computer simulations. And it's genuinely common for a forecast that looks concerning 4 or 5 days out to either sharpen into a confirmed serious threat or ease back towards something far more manageable as the actual event approaches. And forecasters get a clearer, closer range look at exactly how the atmosphere is behaving. That's not a flaw in the science. It's simply an honest reflection of how weather forecasting works at this range, and it's exactly why the responsible approach for anyone in the potentially affected area is to keep watching the forecast evolve rather than treating any single outlook issued several days in advance as the final word on how severe this week's weather will actually turn out to be. If this breakdown helped you actually understand what's behind this week's forecast, rather than just reacting to a scary headline, let me know in the comments whether your area is anywhere near the front. Forecasters are watching. Share it with anyone you know living in the affected region so they have a chance to prepare properly rather than being caught off guard. And subscribe so you're among the first to know exactly how this specific setup evolves over the coming days, because given how quickly these forecasts tend to sharpen as the event gets closer, the picture happening in this exact corridor could look meaningfully different by the time it actually arrives. And that's exactly the kind of update worth catching in real time rather than after the fact. Stay weather aware, stay off flooded roads, and keep that phone charged. Because the atmosphere over the next several days genuinely deserves your attention, and the difference between a forgettable rainy week and a story that ends up in the history books alongside 1974 and 2011 usually comes down to just a handful of ingredients lining up exactly right. Or, thankfully, not quite lining up at all.